Okay, say we have an RLC circuit, but we also include a power source or source of EMF that produces output at some frequency. And we want to ask the question, what is the frequency such that we get the maximum amplitude? So we know that the voltage across the inductor plus the voltage across the capacitor plus the voltage across the resistor plus now the voltage across the power source, that has to be equal to 0. And we want a maximum amplitude. Well, we started with an LC circuit, and we noticed that that was the same kind of equation as the simple harmonic oscillator. Then we introduced resistance, and we found that this involved a dq by dt, right? So this involved a dq by dt term because it's current times resistance. That's the voltage across the resistor. And in terms of the simple harmonic oscillator, that involves a term dx by dt. Right, so that's the dampening term. And now we have a power term. And so this is equivalent to a pendulum, right? Pendulum that swings and that you push the pendulum. And the question is, what is the frequency at which you push in order to get the maximum height? Equivalently, you can think of this as a child on a swing, right? And so you release the swing or the pendulum, and the pendulum comes back, and that's when you push, the mass comes back. That's when you push it, when it reaches its maximum height and momentarily comes to a rest, right? That's when you push it, and then you'll get a greater amplitude. But of course, that oscillation frequency is the natural oscillation frequency of the system. And so the natural oscillation frequency of the LC circuit is just 1 over the square root of LC. So that's the frequency at which you want to set your power source. But we can get there thinking of the child on a swing or damped oscillator. Now let's imagine that we have a power source in a RLC circuit, and that the charge on the capacitor continues to oscillate at some frequency. Let's look at the voltage across the capacitor. Okay, that's just Q over C cosine of omega t by the definition of capacitance. And so notice that when the charge reaches its maximum value, the voltage across the capacitor reaches its maximum value. They both oscillate in the same way, same when they have their lowest value. Now when the charge is 0, the voltage across the capacitor is also 0. So we can say that the voltage on the capacitor, across the capacitor, and the charge are in phase. They increase and decrease together. Let's look at the voltage across the resistor. Well, that's our times current, which is dq by dt, and that gives us a minus omega rq sine of omega t. But let's try to write this in terms of the cosine so we can compare. So that's minus omega rq cosine, let's shift this by 90 degrees, omega t minus pi over 2. But we can also write that as omega rq. Let's try to put in a positive sign, cosine of omega t plus pi over 2. So notice that the voltage across the resistor is not oscillating in the same way as the voltage across the capacitor or as the current. So the voltage across the resistor does not reach its maximum value at the same time as the voltage across the capacitor does, and at the same time as the current reaches its maximum value. So the voltage across the resistor is out of phase with respect to these two components. Let's look at the voltage across the inductor. That's L di dt, which is L d2q by dt, which is minus omega squared L q. We get the cosine back of omega t. But let's try to get rid of this minus sign here, so we can say this is omega squared LQ cosine of omega t plus pi. And we can see that, therefore, the voltage across the inductor is out of phase with everything else that we've calculated so far. Let's look at the current. The current is just dq by dt, so we get minus omega capital Q Q is cosine. So we get the sine. Let's just write this as a cosine. So we have that factor of, we subtract 90 degrees, so we can write the sine as a cosine. But we also want to get rid of this minus sign. So we have omega q cosine of omega t plus pi over 2. All right, so 180 degrees from there. And we can see that the current peaks when the voltage across the resistor peaks. That's not surprising because Ohm's law is obeyed. So there's a direct relationship there. So this gives us a sense of when the voltages, current, and charge are, or how they're oscillating, when each one reaches their maximum value, and so on in relation to each other. So some of these elements are in phase with each other, and some of them are out of phase with each other.